ESA, the European Space Agency, operates several missions in deep space and ensures that they meet their science objectives. Teams of specialized engineers design and deploy the technology needed to communicate with spacecraft that are exploring our solar system.
Lunar track. Max AOS is foreseen in 1 minute. Could you please report once you say carrier lock?
New Norcia, copy. Will go. S-track, New Norcia.
New Norcia, track.
AOS all downlink chain locked. We can see good telemetry. You agreed to connect.
Copy. Thank you very much.
When designing space communication systems, we are confronted with strong constraints on board in terms of mass and power. Therefore, we try to move the complexity into the ground station, where we can build much larger ground stations with much more performance.
ESA has 3 deep space stations around the world, organized in a network called S-track.
We obviously need to receive data from the spacecraft. This is in particular scientific data coming from the instruments. It is navigation measurements, and it is status information from the spacecraft. On top of this, we need to command the spacecraft in order to navigate it and to operate it.
When receiving data from deep space, we want to collect as much signal energy as possible. ESA's antennas are 35 meters wide with the same surface as an Olympic swimming pool. The dish alone weighs 130 tons, and we can point it with the accuracy of 6 milligrees to any position in the sky. The mechanical design makes it possible to compensate for the rotation motion of the Earth. All the received energy is captured by the large dish. It's focused on the so-called subreflector, and the signal is then guided to the base of the antenna, where special dichroic mirrors separate the incoming frequency bands.
Cryogenic amplifiers undertake the critical task of amplifying this weak signal coming from the space using high-tech semiconductor technology developed by European industry to boost this signal around 1 million times or 60 dB. The use of indium phosphide technology and cooling down to -260 degrees Celsius allows to generate only 5 degrees Kelvin of thermal noise, that is only twice the cosmic background noise, the lowest noise you can find in the universe.
The demodulated and decoded signal eventually goes through the Spacelink protocol processing, which outputs the data in a format we can easily handle. This is the telemetry data that includes the low-rate data from the spacecraft platform and the high-rate data from the scientific instruments. Communication also needs to be in the opposite direction. We need to transmit the so-called telecommands to the spacecraft in order to activate thrusters or control our scientific payloads.
Typically, we need to transmit around 20 kilowatts of radio frequency power. This is done using klystrons. Klystron is a high-density energy device that transforms around 100 kilowatts of electrical power into 20 kilowatts of radio frequency power, amplifying the signal some 100,000 times, or what it is, 50 dBs.
The klystron amplifies signals by converting the kinetic energy in a DC electron beam into radio frequency power. The beam is passed through an input cavity resonator, and thanks to a phenomenon called bunching of electrons, in turn produces a high-power radio frequency field in the output cavity. Then, the signal following the same path as the download signals, but in the opposite direction, goes through the beam waveguide, made of solid and dichroic mirrors. It is then reflected by the subreflector onto the main dish and radiated into space. In order to navigate our spacecraft through the solar system, we need to know their position. This is no easy task at planetary distances. Therefore, ESA's deep space antennas perform radiometric measurements that allow us to derive spacecraft position and velocity.
Basically what we conduct is three types of measurement. We range to the satellite. Today we are able to resolve the distance of the satellite within 1 meter. We measure the radial velocity of the satellite with respect to our antenna to an accuracy which is below 0.1 millimeter per second. We can also measure very precisely the angle under which the satellite is seen. By combination of the three techniques, we are able to localize the satellite in a box of hundreds of meters to a distance between the Earth and Mars. This is especially important during certain critical phases, where you want to inject a spacecraft into a planetary orbit.
To achieve this level of precision, special range, Doppler and interferometric techniques are used, which rely on the stability of our ground clocks, typically 1 second deviation in 100 years.
We equip the antennas with very stable clocks, which are based on atomic transition, like hydrogen-based masers, which are able to behave in an extremely stable manner along the propagation time of the light across the measurements. These are times which range above or in the order of the hour. And during this time, the antennas must behave in a very stable manner.
Another important aspect is time synchronization. We constantly need to synchronize the clocks on board our spacecraft with the universal time coordinated we have on Earth.
The data received from the satellites must be assigned at the ground station, at the antennas, with a precise time tag. This time tag is required by the scientist to put in relation the data which is received by the satellite with their scientific models.
So our deep space network is built according to internationally agreed standards for covering radio frequency modulation, telemetry coding. This enables us to give cross-support to external agencies such as JPL, the Chinese, Russians and Japanese. Here we have a ground segment reference facility which we use to replicate the same configuration that we have in our deep space network. In addition, we have a Faraday cage which we use to mount the flying transponder, and onboard data handling system which we use to make representative compatibility testing for the flying missions.
ESA's deep space stations work at different frequencies, up to 34 gigahertz. The new challenge in space communication is optical communication, in particular in the infrared domain at 1 to 1.5 micrometers, corresponding to 200 terahertz.
Optical space communication direct to ground through the Earth's atmosphere is much more challenging because A, the beam is much narrower, and B, the atmospheric effects are much more prevalent. By the way, the narrow beam and the higher frequency is what gives us the high data rates. Based on ESA's heritage from the early days with Artemis and Spot 4, and the current generation of space terminals being deployed on EDRS and Sentinels, we will be able to build deep space optical communication systems.
ESA already operates an optical ground station laboratory at Tenerife, which will be used for the first time to demonstrate optical deep space communication from a spacecraft orbiting the Moon. Optical technology will allow unprecedented data rates from deep space, thereby maximizing the scientific return and enabling new types of missions, like planetary remote sensing as we are used today from Earth.